Hello everyone. In this video, we're gonna solve the Titanic classification problem, which is a very popular problem when you're a beginner. This is a common problem. All right. So the libraries that we're gonna use are mainly scikit-learn, pandas, which you're familiar already. But now we're gonna add stats models. This one I like it, especially because it offers a lot of statistical information. Like it gives you a little bit more in comparison with scikit-learn. Scikit-learn is really good because it's fast, it's simple. Stat models is not that fast, but it offers more information for some models. Okay, so let's talk about the Titanic problem. So here the idea is to predict whether a passenger is going to survive or not. That's our y variable, which we have it here, survived. 0, no, 1 means yes. And we have different features or variables to predict if that's going to happen, if the passenger is going to survive or not. Some of the features are the gender, the age. We have some variables related to the persons that are traveling with that passenger, like number of siblings, spouses, number of parents or children aboard. That will depend, of course, whether the passenger is a kid or if it's an adult. We also have the fare, the cabin, the cabin, the embarked. Okay, so once we load the data, we're ready to go. So the first thing that we do here is to we clean the data real quick. There are some variables where we have a lot of missing information. So let me show it to you real quick. So once we load the data, the first line, we're loading the data. So let me show you. Let me show you the amounts of missing data. So there are like around 800, almost 900 observations, 800 to 900 observations. So for that data frame, let's check the number of missing values per column or per variable. Is here. I was showing the data frame. Okay, so here. So we have, for example, for age, there are 177 observations that are missing the age. And for the cabin, it's like, like more than 50% of the data set is missing that information. We have only 800 observations. So that's why I decided to remove this variable. Because, yeah, it's I mean, to do an imputation to more than half of the data set, that's way too much. In the case of age, it's up to you. Yeah, you can kind of use some imputation techniques. I'm not going to focus on that part in this video. I'm going to focus mainly on the classification effort. So that's why I'm just dropping the cabin. Be careful because the order matters here. I'm dropping the cabin, the column, and removing, and then I'm going to drop the missing values. Why the order is important of these two operations? Because if you drop the NAs from the complete data set before dropping the column of the cabin, that's a problem because you're going to remove like the 687 observations right there. But here I'm just removing the column and then I'm going to remove some of these. So it affects, like less the data set. So the order is important, just be careful. Okay, so once I have the data set, then I split our data. Remember, I'm gonna keep a test set or validation set if you wanna call it. So 80% for training and 20% for testing or validation. Okay. So that part is done. This is our data set. This is how it looks. So we have the passengers and all the information. All right. So here I'm using logistic regression from stat models. That's why we need to type the model first. Oh, let's fix it later. Okay, the model first. So I'm using SMF. That's the alias that I define for stat models. Then the logit function, because that's for the logistic regression. And this is how it works, this SMF library, you need to type the equation. So survive is our y variable. Then this depends of the following variables. These are the features. So we have the age, sex, serial spouses. We have P class. P class refers to, if it's like executive or economy class. But here the coding is in numbers, so you gotta be careful because Python, unless you define that that's a categorical variable, Python is going to assume that this is numeric, right? Because it looks numeric, 1, 2, 3. But again, this is just a number because perfectly, maybe 1 is just like executive, right? And 2 is flexible, and 3 is economy class. So these are labels, they are not numbers. This is not a measurement. So how can you distinguish between a numeric and a categorical variable? Well, numerical variables, typically they are found or computed while measuring something or counting something. In the case of the categorical variables, it's just an attribute. It's based on observation, right? On the characteristic of that specific variable and the different levels. All right. So P class, then you gotta be careful because if you just type P class, Python is gonna assume it's numeric. So in order to define a P class as categorical, I can use here the uppercase C, right, with the parentheses, and that's how this library works. It's not the same remember for scikit-learn. Typically we use like one-hot encoding, and that's gonna be it. But no, for this one, it's gonna recognize if that variable, the values, you have text, then immediately it's gonna assume it's a categorical variable, of course. But if it's numeric, if it looks numeric, even though it's categorical, then you need to use the uppercase C, like here. All right, we have the rest of the variables. The data is coming from Titanic dataset, and we fit the model, and then we print the model summary, right? So we get a summary, and these are the nice things about stat models. It offers you a lot of information about the logistic regression. Here we're using logistic regression. So remember that in the logistic regression, the output initially is the probability that y is equal to 1. In this problem, the outcome is the probability that the passenger is going to survive, right? So before I use this model, I need to kind of like check the variables and to see which of these variables are important or not. So here we have some coefficients. This is not a linear regression, it's a logistic regression. So interpretation, you just gotta be careful, but you will see that the idea is similar. Okay, so we have the intercept, that's beta 0, right? And we have, for the categorical variable, we have different labels here, and we have other numeric variables. Now, how can I know that a variable is significant, is important or not? Well, for each of these rows, there is a hypothesis testing, and the hypothesis test, the null hypothesis is that the beta is equal to 0. So let me write it down. So let's do it for h. So for h, this is how it looks. So there is a null hypothesis that the beta for h is equal to 0. That's the hypothesis. That's the null hypothesis. And the alternative hypothesis, of course, is the complement, right? It is that the beta for h is different than 0, right? So when our variable is gonna be significant, so it's gonna be significant if we reject the null hypothesis, right? Why? Because if you reject that beta is equal to 0, it means that it's different than 0, right? The alternative hypothesis is true. Therefore, that variable is important for in your model. Now, if you do not reject the null hypothesis, meaning that beta equal to 0, then that variable is not relevant. You can remove it from your model. Okay, so you have this, and you have this hypothesis testing for each row in this table, you have, like for beta 0, for this beta 1 or beta 6, for every single beta you have that test, right? Now this is the p-value. This is the p-value in this column, right? This is the p-value. Now the nice thing about the p-values is that regardless the test that you're using, doesn't matter if the p-value is smaller than alpha, then you reject the null hypothesis. So I'm going to assume that I'm working with a 95% confidence level, meaning an alpha of 5%. So if the p-value, this column, there is a value that is lower than 0.05, then we reject the null hypothesis. Therefore, for example, for these coefficients, please notice that the p-values are very small, close to zero, right? They are smaller than 0.05. They are smaller than alpha. That means that we reject that these betas are equal to zero. Therefore, they are important in our model. Now, in which cases, or for which variables, the p-value is greater than alpha. So, for example, the embarked, please notice that p-values are greater than 0.05, 0.3, 0.4. Then that means that betas are equal to zero. We are not rejecting on betas, those betas are equal to zero. Therefore, those variables are not adding value to our model. We can remove them. Right? Same idea with fair, parch. So my advice is just remove one by one. There is no like a mathematical rule to do that, but you can start with the variables with with the highest p-value. That's one option. Or also you can remove those variables with a p-value greater than alpha, and that you as as an expert in the context, that it's not that relevant. So you can do that too. Again, it's not a mathematical criteria. It's more about common sense, right, and the context. So I'm gonna start removing embarked. I just delete the variable from the equation. I rerun this, and again the parch and fair are not significant, so I'm gonna remove one of them. Parch. Let's remove parch. And finally, if you notice all of them, the p-values are less than 0.05, like 5%. Therefore, these are significant variables. So I'm going to use this model, right? And that model, the prediction, remember, it's giving us a probability, but we need to translate the outcome from a probability to a class to make the prediction to find y hat. Then, in order to do so, let's test what's going to happen if we assume our threshold, that's how we call it, equal to 0.05, equal to 0.5, I'm sorry, to 0.5. So if the probability is greater than 0.5, then our y hat is equal to 1. That means that the passenger is going to survive, but it's less than, if it's less equal than 0.5, then we will say that our passenger is not gonna survive, it's gonna die, right? So this is how it looks when I apply this rule with the 0.5, which is arbitrary here. So let's see how it works. So for the first passenger in my data set, Ada Mary Worth. So it's a female, class 2. We know she survived. So the prediction of our model, the probability is 0.74 is high. Since the probability is greater than 0.5, right? That's why the prediction, the y hat, is equal to 1, because that's the rule that we created here, right? So for a threshold, we compare with the probability, and then we make the prediction 1 or 0. That's for binary classification. In this case, it makes sense, right? Female. Now, how do we know that it makes sense? Because we can analyze the coefficients. So for the significant variables, what is the interpretation here of the negative or positive? So, for example, for male, if the sex is male, the coefficient is negative. That means that it's going to reduce the probability of surviving. Same idea with age. As the age increases, it's gonna reduce the probability. And if you remember, from movies, like the when there is a problem with the ship, then the women and kids are gonna get like the highest priority to leave the boat, right? Therefore, it makes sense, right, that they have a higher probability of surviving. A similar idea with the classes. So P class 1, which is not here, it's in the intercept. The level that you don't see here is in the intercept. So in this case, class 2 and 3, the probability is going to decrease compared to class 1. All right, so then it makes sense for the first passenger, which is female, right, mid-age, to have this probability that high. All right, so remember I cannot evaluate one by one because there are too many observations, but we need to analyze the performance of this logistic regression or classification algorithm in general, right? So if you want to do that, then that's when you create a confusion matrix, which is here. This is going to summarize how good is your model doing. So you have, in this case, in the rows, we have the Y, like passengers that survived, that's 1, and passengers that did not survive, that's 0. But this is the real data in the row, right? And in the column, we have the prediction, Y hat, right? Y hat is in the column. So in the diagonal is where we have the right predictions. Where you have the 0, 0 means these are our correct predictions of passengers that did not survive, and the 166, this is our correct predictions for the passengers that did survive. Okay, so we can start measuring, remember the metrics, accuracy, the diagonal. We can measure the recalls or precision the recall or sensitivity and specificity, which are pretty much the same. It's like for the real values, how many were classified correctly for the zeros and for the ones. So we can get all the information from the classification report. It requires only 2 parameters. It requires the real value, Y, that's given in your data, and the prediction. So with these 2 pieces of information, it can be, we can find the metrics. So recalls, precision, and this is the accuracy. What is interpretation? 81%. 81% means that in our data set, we're classifying correctly 81% of the observations. The recalls, what's the interpretation? For 0, the passenger that did not survive, so we're classifying correctly 86% of the passengers in the data set, and 74% of the passengers that survived in our data set. So that's the recall. And the precision is about quality. So when our model said that passenger is not going to survive, it got right 83% of the predictions for that class. And for the class equal to 1 or passengers that survived, our model, the precision was 77%. Okay? There are other metrics like the F1 score that combines recall and precision, right? So the greater the better. You want that value to be high, close to 1. So in general, this is a decent model, like 80%. And these recalls are not unbalanced. Same thing as precision, they are close to each other. Okay, now remember that in this problem we use an arbitrary threshold 0.5. But let's see in general how can you compute or find a better option. So for that, we're going to use the ROC curve. Remember, it has in the y-axis the sensitivity, and in the y-axis 1 minus the specificity. In the x-axis 1 minus the specificity. So in the y-axis we have the true positive rate, and in the x-axis we have the false positive rate. This is 1 minus specificity. So we can compute that. There is a method, ROC curve, right, from scikit-learn, that will give you different thresholds. So these are values for, remember, that we use here to find y hat, right? So initially we assume 0.5, an arbitrary value, but here with this method, we are evaluating multiple thresholds, like, like 0.1, 0.05, 0.2, 0.25, like different values. And for each value, you can get predictions, you can get a confusion matrix, and you can get performance metrics. And that's what we're doing here. So with that information, you can create the ROC curve that you see here. So let me zoom out a little bit like this. So again, in the y-axis sensitivity, x-axis, we have 1 minus the specificity. So the idea is to be, like close to the left, top corner here. This is like the ideal point here, the 1, 0. The 0, 1 is the ideal point here. You have perfect sensitivity and perfect specificity in this point. So we need to find a threshold that is going to get us close to that. So there are different metrics and things that we can do. Remember that one metric is the area under the curve. So for our ROC curve, we can measure the area below that curve. The maximum value is 1, and we got 0.86, which is good, is high. So if it's 0.8 or more, our model has a potential to be a good model. It will depend on which threshold you pick. Now, let's pick our threshold. So we're going to use this rule here, Jordan. So we want to maximize this, the sensitivity plus specificity. So if this value is high, that means that the threshold is good. So it's trying to balance, sensitivity and specificity to get, something high. So we find the best threshold, the maximum value. And in this case, if you notice, close to 0.5, so our results won't change that much. So with the probability of 0.51, we're going to use this to find the y-hats, because it says that it's maximizing this metric, sensitivity plus specificity. So let's do that. So here I'm creating the predictions, the y-hats, for the new threshold, the best threshold that we just found, the 0.51. This is for the training set. This is just to get an idea. But remember, at the end, we need to evaluate this in the validation or testing set. So we create the confusion matrix, which is here, and then the classification report. And we get similar results. Accuracy, it increased a little bit. It was, you remember, in the training set, it was like 0.8, but now it's 0.82. It was 0.81 before. Now it's 0.82. And we have similar recall. Maybe this one decreased a little bit, and similar precisions, right? So now we can let's test our logistic regression with new data. So the accuracy, it remains similar, 0.80. And the recall, it's dropping a little bit for this one, for the passengers that survive. In the case of the precision, it remains similar, but yeah, the recalls, we see a distance here. So these are the things that you need to see and to make decisions, like how to, what can you do? Now, this makes sense if you think about it, because initially our threshold was equal to 0.5, right? So if it's greater than 0.5, then we say that y-hat is equal to 1. But we increase a little bit the threshold from 0.5 to 0.51, right? A little bit. So now what we're doing is that we're reducing the number of observations with a y-hat equal to 1. If you think about it, that's what's happening. We're reducing the number of observations with a prediction of equal to 1. So that's why now we are predicting less, or our recall for the ones was reduced. Most likely it improved the precision, but it affected the recall because we're increasing the threshold a little bit, right? Okay, so that's how you use the logistic regression. And the idea of this video was to go over a practical problem. You can find the link to this notebook below the video. I will see you in our next lecture.